Okay, so good afternoon or good evening or good morning. So my name is Tori Yamada, and on behalf of this JAXA science team for the Lunar telescope activity, I'm trying to discuss about the uncrewed operation of the pressurized rover for Decameter Lunar telescope at TSUKUYOMI. TSUKUYOMI is actually the code name of a project, which means the god of the moon in ancient Japanese myth. So next slide, please. So this is, in summary, what we are thinking about is deploying multiple, more than 10 radio antenna units on the lunar surface to observe the so-called global signal of the neutral hydrogen in the very early stage of the universe that is called a cosmic age. So by utilizing this pressurized rover uncrewed operation, there are some advantages to deploying such multiple units in one mission, and also utilizing some potential cargo mission to bring these multiple antenna units to the moon. Okay, so but let me start with the discussion of the scientific goals. So next slide, please. Okay, so our science goal is to detect the signal of the neutral hydrogen in the very early phase of the universe, which is called dark age. Is before that is a phase before the formation of the first stars or galaxies in the universe. So this, say, first 100 million years, it conserves a very pure and clean probe information for the very early phase of the universe, which means it offers a very clean probe of the fundamental cosmology. And I'm gonna explain, but this feature is seen in a very weak but broad absorption feature in the cosmic microwave background radiation at around, say, 15 megahertz in frequency for the radio observations. So next slide, please. Yes. So as you know, there's a hyperfine structure transition of the hydrogen, and which corresponds to the photon wavelengths of the 21 centimeter or the frequency of the 1.4 gigahertz. And this is by the cosmic redshift in the early universe. For example, the cosmic redshift of the 30 to 200, this frequency is shifted to 7 to 40 megahertz, or several tens of megahertz, I would say. And so this feature is seen in the weak absorption in the cosmic microwave back radiation of the 3K. So the very weak, I mean, about just a 40 millikelvin broad absorption feature. And the global signal is the so-called sky average signal of this spectrum. And but in order to detect them, we also have to think about the very bright foreground emission by our own galaxy, Milky Way, which is very, very bright. Okay, next slide, please. Yes. So we made a study to reach the concept of the so-called short dipole antenna concept. Short means the length of the dipole antenna is smaller than the wavelength, significantly smaller than the wavelength of the this radio emission. For example, for the wavelengths to 6 to 300 meters, the length of 5-meter antenna is considered. And for the frequency coverage, this antenna has a very frequency-dependent efficiency, which is shown in the second and the third panel in this figure. And but this is very good to compensate the frequency dependence of the foreground radiation of the Milky Way, which is shown in the leftmost panel. So as a result, we're going to have a fairly flat output power spectrum on the frequency. Okay, next slide, please. So in very short, we reached some concept with this short dipole antenna solution with a 5-meter length of the antenna, and which is put say about 7 meters in the height from the moon. This height is to avoid the effect of the lunar surface to our beam, and with some dielectric constant still somewhat uncertain. Okay, next slide, please. So we studied so how many these antenna we need to detect such global signal of the cosmic dark age. And in short, we need more than 10 such antenna units to detect the signal with stable and fairly long time observations at the lunar surface. Okay, next slide, please. How to achieve this? So we are now in the study to step to further realization of this project in the step-by-step manner. So as a first step in a roadmap, we would like to conduct as a demonstration mission, which is we call it the prototype antenna system. So antenna and the receiver system as a payload of some possibly a commercial lander. And so in this case, power and communication provided by the lander and only daytime operation to make the demonstrate the capability of this detection of the radio emission from the sky on the moon, and to confirm the system calibration and the characterization, and also to detect the Milky Way signal. And this concept design is being proceeded under the JAXA front-loading program for the science on the lunar surface. So next slide, please. Yes, and this detection of the global signal is not our own science goal, but how should I say, it is very important, more humankind-like science goals. So there are many missions and also concepts developed so far in many countries, including US. And also we recently heard some likely detection of the Milky Way radio emission by the Rolls-S1 project. Okay, next slide, please. So this is a summary. If we compare our TSUKUYOMI with the previous concept study of the far side in the US, and also the concept, the mission of the Lucy Night, which is, I think, being studied for the expected launch in the 2026. So this is very similar with some different parameters, but in any case, to detect the global signal, we need we need to deploy multiple units, likely more than 10 such antenna units on the moon. Next slide, please. So there could be a possible trade-off between how to deploy such 10 antenna units on the moon. One is lander type. The other may be the so-called rover carried type, which may utilize the pressurized rover. Next slide, please. And we understand the pressurized rover is on the South Pole, and near the South Pole. And of course, the putting the radio telescope on the moon have the merit advantage to avoid the artificial radio emission from the Earth at the far side of the moon. But at the far side, there's also, we face the very, very bright Milky Way emission on the sky. So there should be some trade-off between which is better, the South Pole or the very far side. Next slide, please. So with the cooperation with the JAXA PR team, we made a kind of feasibility analysis for the uncrewed operation of the rovers. So we may reach 82 degree in south by the 6 months operation of the uncrewed operation of the rover to putting the antenna to such a places. Next slide, please. And of course, we need lots of potential things we need to consider, including the potential cargo mission and how to what is the loading operation from the cargo to the lander, to the rover, and also rover loading platform and the deployment mechanism. Such kind of things we need to study right now. Okay, the next slide is the final slide. So in summary, we are discussing to deploying more than 10 antennas on the lunar surface to detect the global signal of the cosmic dark age of the neutral hydrogen. Thank you very much.